So in chapter 15, we've looked at chemical equilibrium, and we're going to continue to kind of see that through this chapter, but we're going to be focused on acids and bases specifically in chapter 16. And with acids and bases, these are going to be something that we deal with on a daily basis. So if we just look here, this is just a soda label. We can see phosphoric acid, citric acid. So we can see some of the beverages we're going to include these. Cleaning products are going to have bases in them. So if we look at just the table here, we can see some common ones. And then the same thing with the acids on the right-hand side. So even something like aspirin is going to be acetylsalicylic acid. A lot of fruit is going to contain citric acid. And then even vitamin C is ascorbic acid. We'll see exactly what makes all of these acids acidic, what the definition of those are. And then, like I said, with the bases, a lot of those are going to be used in cleaning products. So you can see your drain cleaner, ammonia, and then just a bunch of other things. And then environmentally, these are going to be important, especially with the acids, because of acid rain. So if we look at the picture here, we can see the power plant. We're going to have some sort of combustion occurring. So it could be coal or some other fossil fuel. But we're going to be combusting it. And then with that, there's also going to be sulfur mixed into those fuels. So we're going to wind up producing sulfur dioxide. And then similarly with automobiles, they're going to be producing nitrous oxide, so NOx compounds, NOx, with the X as the subscript, because we can have the nitrogen and oxygen in different ratios. But we're ultimately going to see sulfur trioxide and NO2 are going to combine with water to give us sulfuric acid, and then nitric acid as well. So when the rain then precipitates down, they're going to be bringing those acids with them. So that's where we get acid rain from. And then that's going to be problematic environmentally, because if we look at the picture, we can see the example. We're going to have that rain precipitate down, and then it's going to run down into the rivers, the streams, lakes, and things like that. And if the lakes and streams aren't buffered, which essentially just means resistant to acids and bases, what we're going to see is that environment's going to become extremely acidic, and it's just not going to be something that those organisms can survive in. And then acid rain is still an issue. So you may have seen in like a textbook or a picture, you may have even seen it in person. The acid rain can actually do damage to statues, depending on what it's made of. So sometimes you'll see the statue kind of has its sort of like its face worn down, just because the acid rain is going to eat away at the substance in the statue itself. And then similarly with buildings. But this acid rain has declined in sort of the damage it can do, because we've been able to better combat the SO2 production and the nitrogen oxygen compounds as well. Because with cars, we've got catalytic converters, which help take these NOx compounds and convert them into just elemental nitrogen and oxygen. And then they also do that with carbon monoxide. They help convert it to carbon dioxide, which is carbon monoxide is just a product of the incomplete combustion that can occur in the internal combustion engine. But then with the power plants as well, in some cases we can prevent these substances from even making it into the atmosphere. But also there's what's known as clean coal, which is very misleading, because it's still going to be coal. It's still going to contribute to greenhouse gases, global warming. But the reason it's called clean coal is because it's going to have a lower amount of sulfur there. So we're going to see less of this SO2 being produced. So we'll ultimately have less of the acid rain as a result. And then with the acids, like I mentioned earlier, a lot of fruits and vegetables and things are going to include acids. So what we're going to see is acids tend to have a sour taste, whereas the bases are going to be bitter. And then another property of bases is going to be that they tend to be slippery. So like I said, they're often used in cleaning products. But if you're ever working in the lab and you've got like a titration or some sort of experiment with a base, if you happen to get that base on your gloves, the gloves are then going to become very, very slippery. And then with it, just to mention, a lot of the times people, especially in like TV shows and things like that, talk about acids and then the damage acids can do if it gets in contact with your person. But bases are also going to have the ability to damage living tissue as well. So we want to be able to, or we want to make sure that we're handling either of these types of solutions with care. But we're going to see when it comes to acids and bases, there's going to be a couple different definitions for what's an acid and what's a base. And the first one is just going to be the Arrhenius model or the Arrhenius definition. So the same name as the Arrhenius equation from the previous chapter. But with this, we're going to see acids are going to be substances that increase the concentration of hydrogen ions when we dissolve them in water. Whereas the bases are going to increase the concentration of hydroxide. So we'll ultimately see neutralization reactions are going to be what we have occur when we take an acid and mix it with a base. And the reason we're going to call it a neutralization reaction is because that acidic hydrogen and the basic hydroxide are just going to combine to make HOH, just H2O, which is just going to be that neutral water. But the second definition is going to be similar. So with the Arrhenius one, we're thinking about acids H+, bases OH-. But with the second definition, this is going to be the Bronsted-Lowry definition. What we're going to see is acids are going to be considered things that donate a proton. And then a proton is just going to be this hydrogen ion itself. So if we think about a hydrogen atom, atomic number of 1, so it'll have 1 proton. It's also going to have that 1 electron to balance out the charge. And for the most part, hydrogen, like 99% of all hydrogen atoms are going to be hydrogen 1. So that'll be all that they contain. But then when we're looking at this hydrogen ion, we've got that positive charge because the atom lost the lone electron, so it became positive 1. And that's why we're going to see a hydrogen ion is going to be the exact same thing as a proton. So sometimes it's a hydrogen ion donor, sometimes it's called a proton donor, but those are going to be synonymous terms. And then if the acid is donating that proton, we're going to see the base is just going to be the thing that accepts it then. And then with these definitions, we're going to see that there's six substances that we consider to be strong acids. So we can see the formulas there. And you can see the similarity between all of them is we've got that hydrogen out in front. That's going to be the acidic hydrogen that ultimately dissociates, gives us that H+ in solution. And the reason we're going to consider these to be strong acids is just because these substances are going to completely ionize. So if we took a hydrochloric acid molecule, HCl, if we take it and place it in water, what we're going to see is 100% of that is going to dissociate into H+ and then that negative chloride ion. And that's why we're going to consider this to be strong. We're going to get 100% of that hydrogen ion. We're going to see with other substances, we're going to consider them to be weak acids because they're still going to increase the concentration of H+. But we're going to see in that case, we're actually going to have an equilibrium. And most of the acid is going to actually stay as the molecule with only a little bit of it dissociating there. Yeah. But if we look at the picture we have here, we can see why HCl is going to be considered an acid in terms of the Bronsted-Lowry definition. And I should also mention H3O+, this is going to be the hydronium ion. This is the exact same thing as a proton. We're just now showing it instead of H+ by itself. We're just essentially showing that proton attaching to the water molecule that it's dissolving in. But that H3O+ and the hydrogen ion itself, you can more or less think of them as the same. But this is going to be or we can use this to see why HCl is going to be an acid, because in this case, it's going from HCl to that chloride ion. So it's donating that H+. That's going to be our definition for an acid. And then with the water, it's going from H2O to H3O+. So it's taking on that hydrogen ion, it's accepting that proton. That's why we would, in this case, consider water to be the base. And we'll actually see water, depending on what we have it with, can be an acid or a base. Oops. But like I said, with the strong substances, they're going to completely dissociate. We're going to see in the picture here, this is HNO2. So on one of the previous slides, we had the 6 strong acids. HNO3, nitric acid, was one of those. But this is nitrous acid, HNO2, so it's going to be a weak one. And that's why we actually have this equilibrium here. We've got the forward and the reverse reaction. Because in this case, the HNO2 is only going to partially dissociate. So we're only going to get a little bit of the H3O plus or the hydrogen ion, and a little bit of that nitrite ion, but most of it's going to stay as HNO2. But with this one, we can see why this is going to be considered an acid. So I'm just going to do A for acid, because it's donating that proton. And with these Bronsted-Lowry acids, and bases as well, we're going to see that there's what's known as conjugate acid-base pairs. And when we're looking at it, we're going to have the acid and the base on one side. We're going to have the conjugate acid and the conjugate base on the other. When we go to have those sort of related to each other, what we're going to do is just look at the other side of the reaction and find the formula that looks similar. So in this case, HNO2. And then we've got NO2 minus on this side. And then since the nitrous acid is our acid, what we're going to consider this NO2 minus to be is just our conjugate base. And then when we look at the water, that means the H2O has to be our base, and the hydronium ion has to be our conjugate acid. And the reason we have the acid base with the opposite thing on the other side is because when we look at it from left to right, HNO2 is donating that proton. So HNO2 is an acid. H3O plus, or H2O rather, is going to H3O plus, so it's accepting that proton. That's why it's a base. But now if we go right to left, H3O plus is donating a proton, so it's actually acting as an acid in the reverse reaction. So that's why we've got the conjugate acid-base pairs. And then the same thing, just kind of opposite with the nitrite ion, NO2 minus, it's accepting a proton going from right to left. So that's why we would actually consider it a base in that direction. So again, with these conjugate acid-base pairs, we're just kind of looking to see what the similar formula on the other side is. And then we can take, just kind of determine if it's accepting or donating a proton. That'll determine if it's an acid or a base. And then on the other side, we'll just have it paired with the other thing. So again, since we've got acid here, the NO2 minus is going to be our conjugate base, and then just the reverse for the base and the conjugate acid. Yep. You can see that a little bit better here. I forgot I had this on the slide, so it would have been easier just to do this, but all right. So with this, see if you can take these 8 examples, and for the first 4, we want to determine what the conjugate base for each would be. And then for the second 4, we're going to do the same thing, but we're going to say that these are going to act as bases. So we want to figure out what the conjugate acid is. So what we need to do is think about what an acid's going to do. Is it going to donate or accept a proton? And then we can change the formula accordingly. And then the same thing for the bases on the second 4, it's just going to be the reverse in that case. So take a moment to kind of go through those on your own. But I'm just going to start going through it now. And with the acids here, so these first 4, these are all going to donate a proton, so they're all going to lose a hydrogen. But since it's a proton, it's losing that positive. We're going to see each of these is going to become one, it's going to become slightly more negative. So in this case, we'll have ClO4 minus, we'll have HS, and then again, that's minus. The third one, in this case, it's going to go to neutral because we already have a positive charge. So we'll just have pH3, that neutral compound. And then for the HCO3, we'll actually see this one can act as an acid or a base. But since we have it acting as an acid here, whoops, don't want the hydrogen there. But since we have it acting as an acid, we're going to have it donate that proton, get rid of that hydrogen. So we're just going to have CO3. And then since it's already -1, the conjugate base is just going to have a -2 charge there. And then for the second set, again, in this case, we're going in the opposite direction. So these four are going to be bases. So they're going to accept the proton. So we'll have the substance gain a hydrogen as well as a +1 charge. So we'll see in this case, cyanide is going to become hydrogen cyanide. The sulfate ion, will gain that hydrogen as well as a +1 charge. So we'll see it'll ultimately just be -1 now since it's starting with the -2. Water, went in the opposite direction there. Water, since it's acting as a base in this case, is going to accept that proton, so it's going to become hydronium H3O+. And then again, with the final one here, it's the same as the last one in the previous set. It's just in this case, now it's acting as a base, so it's actually going to accept a proton, and it's actually going to become carbonic acid for its conjugate pair. But again, with the acids, they're going to donate a proton, so they're going to lose H+. The bases are just going to be the opposite. They're going to accept that proton. But the formula, we can just change it by including that hydrogen and then changing the charge slightly, or removing the hydrogen depending on if it's an acid or a base. Oh, and then similarly, so kind of like the previous example, we had the HCO3- that could act as an acid or a base, could accept or donate a proton. We'll see the same thing with the hydrogen sulfide. So amphiprotic just means it can accept or donate a proton. And we can have the we can have the hydrogen sulfide ion, HSO3, do the same thing. So we can actually have two different reactions with water, and then depending on which is acting as an acid, which is acting as the base, the movement of that proton is just going to be reversed. So for the start, we can just have the same thing for the reactants and just the reactants rather. But like I said, in one case, we're going to have the acid for that hydrogen sulfide. And the other will have a base. So A on the top, that'll be our acid, which means the water is going to be a base in that top one, and an acid in the second one. But with it, if we think about it now for the acid, it's going to donate that proton. So we're going to see the acid get rid of that H+. So we'll have the sulfite ion, SO3, 2- now, which means we'll have to have the hydronium ion, or that water accept the proton to become hydronium. And with it, if we check the balance of charge, the conservation of mass, we still have the same thing on both sides in terms of mass and charge. So this is an acceptable reaction in that case. And again, it's just the acid here because it's donating the proton. So for the second one, we're going to have it in reverse. Now water is going to lose one of those protons. The hydrogen sulfide is going to accept it. So we'll see we'll have H2SO3 will form sulfurous acid. And then that'll be neutral because it's -1 to start. It's gaining that +1 charge. And then we'll also just have that hydroxide ion now. And with it, because I forgot for the first one, since the hydrogen sulfide's acting as an acid on the opposite side, that similar formula is going to be our conjugate base. And that makes sense because if we go in the opposite direction now, SO3 2- is accepting a proton, so that's going to be our definition of a base, which means the hydronium has to be our conjugate acid, and then we'll see just the reverse on the bottom. We'll actually have sulfurous acid and then that hydroxide ion. Yep. And then with this, what we're going to see with this table here is the strength of the acid or the base gives us information about the relative strength of the conjugate pair. So if you look at the left-hand side, those top few are going to be very strong acids. So a hydrochloric acid, sulfuric acid, nitric acid. And then on the opposite side, the conjugate base is going to be a very, very weak base. And if we think about why that is, if we had Cl minus here, HCl wants to completely dissociate. So that chloride ion isn't going to be a very good hydrogen or proton acceptor. Same thing with the hydrogen or the HSO4, the nitrate ion. These acids are going to stay completely dissociated. So we're not really going to see these actually even accept the proton at all. That's why when we looked at the very first sort of reaction we wrote, it was just that single arrow, because it's going to completely dissociate. Same thing with the bases, just in reverse. The conjugate acids are going to be extremely weak, just because they're not going to accept that proton, or they're not going to donate that proton, excuse me. Yeah, so with the methane, for instance, it's never going to really ever donate the proton to become CH3 minus. And then with the middle ones, where we've actually got our weak acids and weak bases, that's going to be where we kind of see more even strength in terms of the conjugate pairs. But if we look at water, we'll actually see if we have two water molecules, we could have one of them act as an acid, one of them act as a base. And this is going to be the autoionization of water, or the self-ionization of water, because the water molecules themselves are going to be ionizing each other. And if we just kind of look to see what's happening here, the lone pair on the oxygen, so it's got those two lone pairs to give it a full valence shell, because it's got two electrons in each of the bonds as well. So it's got 8 electrons total, or 8 valence electrons total. But the lone pair of the oxygen is going to attract the positive hydrogen of another. And if we think about where the electrons are shared in this bond, it's going to be between the hydrogen and the other oxygen. So this hydrogen is going to be kind of exposed, and that's going to be one of the reasons that hydrogen bonding is going to be so strong. But what we'll see in some cases is the electrons there are essentially going to pop off the hydrogen ion, and then the 2 electrons in the bond are just going to stay with the other oxygen. And that's why we see, in this case, H3O+, because we gain that hydrogen proton, but we didn't also include the electron with it. So it's just that H+ going there. And then the electrons themselves are still staying with that oxygen. So we've got OH- for the other ion there. And then with these arrows, they're essentially just showing the movement of the electrons. So in this case, the 2 electrons in the lone pair are forming a bond with that hydrogen. And then the 2 electrons that are already in this bond are just staying with that oxygen. So that's just what the electrons are showing there. Sometimes it's known as pushing electrons, but they're just showing sort of what's occurring with the electrons themselves. And then amphiprotic is a substance that can donate or accept a proton. Amphoteric is going to be a substance that's capable of acting as a acid or a base. So an amphoteric is more of a more general term. But the self-ionization of water is actually going to be at equilibrium, or create an equilibrium. And with Kw, this is just essentially the equilibrium expression for the autoionization of water. And like any equilibrium constant, it's going to be temperature dependent. So this is going to be for 25 degrees Celsius. The concentration of the hydrogen ions times the concentration of the hydroxide ions are going to give us a product of 1 times 10 to the negative 14th. And this is going to be important because this is actually going to allow us to determine the concentration of these ions, as well as the pH. So how acidic or basic a substance is. But if we think about the equilibrium expression, we never include pure liquids. We never include solids. It's just either solutions or gases. So when we look at the Kw, that's why we don't have H2O at all near the bottom. So it's still products over reactants. These ions are our products, those go on top. But with the reactants, it would just be H2O liquid. So it wouldn't get included in the equilibrium expression. So we could really think of it as over 1. And that's why we just don't have to include anything in the denominator here. But with that in mind, see if you can determine what the concentration of hydrogen or hydroxide ions and the proton, that hydrogen ion, are going to be in a neutral solution at 25 degrees C. So with that, and we can actually think through this one together, but with that, we're going to have the concentrations of these two equal to 1 times 10 to the negative 14th. And if it's a neutral solution, we'll see exactly what that means in terms of the pH in a few slides. But if it's a neutral solution, it's not acidic or basic, which means we're going to have equal concentrations of the hydrogen ion and the hydroxide ion. And that kind of makes sense because if it's neutral, it's just basically going to be pure water. So for every hydronium ion or hydrogen ion, H+, remember those are going to be the same, we're going to have 1 hydroxide. So for a neutral solution, it makes sense that we're going to have the equal concentration there. So if we want to go through this, we can essentially set the concentration of either of these ions equal to x. So we'll have x squared is equal to 1 times 10 to the negative 14th. And we'll see that the concentration, whoops, I forgot the molarity there. So it should really be capital M for molar. But the concentration of each of these ions in a neutral solution, again, at 25 degrees. This is going to be temperature dependent. At 25 degrees, we're going to see that the concentration of both of those is just going to be 1 times 10 to the negative 7th molar, again, so capital M there, or moles per liter. And then for the next one, we want to do essentially the same thing, but in this case, we won't have equal concentration of those two ions. So it's not actually going to be a neutral solution. It's either going to be acidic or basic. But in each case, we still have that Kw, 1 times 10 to the negative 14th. And then we have the concentration of the hydroxide. So we can plug that into our equilibrium expression and actually determine what the concentration of that hydrogen ion or hydronium ion is going to be. So for this one, again, equal to 1 times 10 to the negative 14th. But in this case, we know the hydroxide ion. So we can essentially just take the Kw, divide it by that concentration, and we'll get the concentration of the hydrogen ion. And for the first one, since we've got a concentration of 0.01 for the hydroxide, we'll see we'll have a pretty small concentration for the hydronium or the hydrogen ion. So this would be a basic solution just because we've got a higher concentration of that OH minus. And then with the second one, we see just the reverse. We're going to have a higher hydronium ion or hydrogen ion concentration. So in this case, we'd have an acidic solution. But again, we can solve for the hydrogen ion because the Kw here, at least at 25 degrees C, is going to be 1 times 10 to the negative 14th. And then, like I said, with the concentrations, we'll be able to use that to relate to the pH, which tells us the essentially how acidic or how basic something's going to be. So if we look here at the chart, we've got pH 0 at the top, pH 14 at the bottom, and then it's telling us more acidic near the top, so lower numbers for pH is going to be more acidic. Higher numbers will be just the opposite. Those will be the more basic. So if we look at some of the examples, gastric acid, just stomach acid, it's going to be very, very acidic because it's going to have a pH of right about 1. And then we can see some other examples. So rain, slightly acidic there. Saliva as well helps with breaking down the food that you're going to be eating. We've got different vegetables and fruits here as acidic, as well as some drinks. So like soda, vinegar is actually going to be, or at least the substance that gives vinegar the smell is acetic acid. And then, like I mentioned previously, a lot of the bases are going to be cleaning products, so bleach, ammonia, um, and then sodium hydroxide is just a strong base itself. So you can see a very high pH there because it's going to be very, very basic. But with this, just if you ever are cleaning anything, just make sure you don't ever mix those cleaning products together. Because ammonia and bleach, for instance, two household cleaners, probably really shouldn't be using ammonia at all. And then I would avoid using bleach if you don't need to. But if you do mix those, it's going to then create a toxic gas. So just never mix the cleaning products. But in terms of how the pH relates to pOH, is they're essentially just going to be the reverse. So in this case, we've got it on a 14, a scale of 14, basically. And since the pKw is going to be equal to 14 itself, if we know the pH, we can just subtract it from 14 to get the pOH. It's essentially the same scale. It's just in terms of if we're thinking about it more acidic or basic, because we're focused on the hydrogen or the hydroxide for the two. But if we do need to calculate the pH or the pOH, it's just going to be taking the negative log of that ion. And we'll see a few examples of that. So with this one, calculate the pH value for a solution in which hydroxide ion is 0.01 molar. So with it, we could use the Kw to figure out the actual concentration of hydrogen ions, and then we could plug it into the negative log of concentration to get the pH. Or we could just do the negative log of the hydroxide ion, get that pOH, and then just subtract it from 14. And then we could do the same thing for this one. We've just got a different concentration of that hydroxide because we're going to have a different pH. But if we look at it, we can plug in negative log 0.01. We get a pOH of 2, which means we've got a pH just of 12. So this is going to be a very, very basic solution. And then I should also mention with the pH and the pOH, the number of digits we include there is going to be a little bit different because we're only going to be focused on the decimal. So in this case, since our concentration had two significant figures, when we go to convert that concentration into a pH or a pOH, we're going to include 2 digits after the decimal. So that's why with the second one, we still, again, have 2 sig figs here in this concentration. So we can still go about converting in the same way, get a pOH of 8.74. So when we convert it, or I should say we've got 2 digits after the decimal there again, so 0.74, because we've got 2 sig figs in that concentration. But when we go to convert this one now, we'll get 5.26, because we can just subtract that pOH from 14 in order to convert it to pH. And then just to go back for a second, one thing I want to point out here is as we change the pH by 1, because it's going to be based on this logarithmic scale, that means we're going to have 10 times as much hydrogen ions if we're decreasing the pH. So if we're getting a smaller number by 1, that means we have 10 times as much or 10 times more hydrogen ions. So if we increase the pH from 4 to 1, that's a change of 3. That means it's actually going to be 1,000 times more hydrogen ions in that solution. Or if we went the opposite direction, we'd have 1,000 times less, or we'd have 1,000 times more of the hydroxide ions. But just recognize that the pH scale, since it's going to be based on the log of the concentration, a change of 1 pH unit is going to represent a 10 times change in the concentration of those ions. And then again, depending on if we're increasing or decreasing the pH, is going to determine if the ion concentration is increasing or decreasing as well. But with the next one, see if you can use the previous equations to figure out if we have a pH of 3.76, what the concentration of that hydrogen ion would be. And with this, we'll have to kind of rearrange this equation a little bit because now we have the pH, So we're solving for the hydrogen ion concentration there. So we'll have to take, divide each side by -1, and then take erase each side. So if we do 10 times negative pH, we'll see that's going to be equal to the hydrogen ion concentration. So in this case, 10 to the negative 3.76 is going to give us our hydrogen ion. And then for this one, since we've got 2 digits after the decimal, that's why I have 2 digits or 2 significant figures in this concentration. So just remember with the pH in terms of like sig figs, we're just focused on after the decimal. And then when it comes to measuring pH, there's going to be a couple different ways we can do it. So in the lab, at least in Gen Chem 1, I don't think we've actually used them in Gen Chem 2 yet. But in the lab, there's going to be pH probes like we're seeing here. There's also going to be different types of indicators that we can use. But when we're measuring pH, we can do it in several ways. So in this case, they've got soda, so you can see a pretty low pH there because it's going to be very, very acidic. So that's why with the soda, it can damage your teeth because it's acidic. And then also with the cans of soda in particular, metal and acid react. So with the metal cans, they have to line it with a polymer just to help make it resistant to that acid degradation. But we can use pH probes to measure the pH of a solution. And with it, it just uses ion exchange. So with the solutions, if it's a acid, we'll have a whole bunch of the H+. If it's a neutral solution, we'll have a medium amount. And then if it's a basic solution, we'll have a little bit of that hydrogen ion. But the pH probe themselves is a glass electrode, and it's going to allow the ions to be exchanged. And essentially what that's going to do is just create a difference in voltage. And the probe itself can measure that difference in voltage and essentially just calculate a pH accordingly. And that's just how these pH probes are going to work. With it, since it is based on the voltage difference, and in some cases different ions, so instead of just hydrogen, if we have like a lithium or a sodium ion, that can actually affect the probe itself. So sometimes they're not perfect, especially at very, very low pHs or very high pHs. But that's just going to be the basic principle of how these pH probes work. They use a difference in the voltage between the electrode and the solution itself. And that's going to be based on the ion exchange. And then it can calculate the pH accordingly. But like I said, there's going to be also indicators. So if you've ever done an acid-base titration in any of your previous courses or lab experiments, you had to use a pH indicator because the acids and the bases themselves are going to be colorless. And then these indicators change at specific concentrations, or specific pHs, I should say. So you can see just a few examples here, and then the colors that are listed are just the colors that those solutions are going to be at those pHs, and then it shows where the color change is going to occur. So depending on where we wanted to see a certain pH change, we could use a different indicator. But the way it's going to work is in these different solutions, we're going to have a different amount of hydrogen ions. And then based on the indicator itself, there's going to be an equilibrium where the indicator is either sort of complex with that hydrogen ion or it's just the free indicator. And we're going to see different colors in those two forms. And that's why we'll have the different colors. And again, the equilibrium itself is basically going to determine what pH or where is that pH going to give us the color change. But with this next one, what is the pH of a 0.04 molar solution of HCl4? So this is going to be one of our strong acids. So with it, it's going to fully dissociate. So in this case, kind of seems like we don't have the hydrogen ion concentration. We don't have the pH. But since we have the concentration of the overall solution, and we know it's going to fully dissociate, this 0.04 molar is also going to be the concentration of the hydrogen ion. So what we can do is just take the negative log of that concentration, and that'll just give us the pH of this solution. So negative log of 0.04 molar is going to give us a pH of 1.4. And again, this is going to be a very strong acid. That's why we can actually have this work. If we had a weak acid, we'll have to kind of go through a similar process to what we did in the previous chapter. But with the bases, or with the strong bases, I should say, these are going to be the same idea where they're going to completely ionize, they're going to completely dissociate. So if we looked at something like lithium hydroxide, when we take that substance and dissolve it in water, we're no longer going to have the lithium and the hydroxide together. They're going to completely separate into just that lithium plus one ion, the hydroxide negative one ion. And then the same thing with the rest of these. It's just in the case of calcium hydroxide, strontium hydroxide, and barium hydroxide, since the metal in each case is going to be positive 2, we're going to need a second hydroxide ion there in order to balance out those charges. So when we take barium hydroxide or strontium or calcium hydroxide and dissolve them, we'll actually get 2 hydroxide ions for every single molecule that we have. But with them, these are going to be our 6 strong bases because they're going to completely dissociate. And with this, we kind of already saw it with one of the previous ones. So that POH is just going to be equal to the concentration of the negative log of hydroxide. The negative log of the hydroxide concentration, I should say. I kind of had that reversed. And then since the sum of POH and pH is always going to be equal to 14, if we know the POH, we're also going to know the pH, so we could actually calculate the hydronium ion that way, or we could use the water solubility or the water KW product. So if we look at the example here, a solution has a pH of 8.71. So when we get our concentration, we're again going to want just 2 sig figs because we've got 2 digits after the decimal here for the pH. But we want to figure out what is the POH, what is the H3O concentration, and what is the hydroxide ion concentration as well. And since we're given the pH, we can just do 14 minus 8.71 to get that POH. And then since we already had the pH, we can get the hydrogen ion, which is going to be the same as the hydronium, fairly easily by just doing 10 to the negative pH. We'll see it's 1.9 times 10 to the negative 9th molar there. And then with the hydroxide, we could do something similar since we just calculated POH. Or we could have also used the water KW value. And we could do 1 times 10 to the negative 14th and divide it by this hydrogen ion concentration. And we'll see we'll get the same number there. So with these, there's a couple different ways that we can approach it, just depending on sort of how we want to relate these different pieces of information. And then also depending on what we're given initially, there may be an easier path to go with certain questions. But like I said, with the strong acids, the reason we're going to consider them strong is they're going to completely dissociate. So that's what we see here with the nitric acid. If we made a solution that was 0.1 molar nitric acid, what we're actually going to have is 0.1 molar hydrogen ion concentration, 0.1 molar nitrate ion concentration, but we won't actually have any of that HNO3. And that's why we show it with just a single arrow, because it's essentially just going to be a one-directional process. But then with the weak acids, so something like nitrous acid, HNO2, we can make that same concentration solution initially, but because it's weak, it's only going to partially dissociate. So we're going to reach that equilibrium. And now we can see we'll have like 95% of it as HNO2. And then notice we still have it dissolved, so it's still AQ, it's just not dissociated. So if we wrote the equilibrium expression for this, and we'll see this is actually going to be called Ka, we'll actually still include this HNO2. But we'll have like 95%, whatever it's going to be for that particular acid is going to differ. But we're going to have the vast majority of it as that full molecule, whereas only a portion of it will be the ions. And then, like I said, this is going to be known as the Ka. So again, it's just that equilibrium. Then we use A to represent the acid. So if we look at the HNO2, we still won't include water because it's a liquid, but we've still got the HNO2, we've got the ions dissolved. So that's why we're going to include all of those other pieces there. So we'll have the ions on the top because those are going to be our products. We'll have the full molecule on in the denominator because it's part of the reactants. But it's going to be the same kind of idea as the equilibrium constants we've seen. So with this example, a student prepared a 0.1 molar solution of formic acid. So this is going to be a weak acid. It's not going to fully dissociate. And measured its pH using a pH meter and found it was 2.38. We want to first calculate the Ka for formic acid at this temperature. And then we also want to figure out what percentage of the acid is ionized in this 0.1 molar solution. So with the pH, what we can do is use that to figure out the hydrogen ion concentration. So we can do 10 to the negative 2.38. And what we're going to see is we've got a hydrogen ion concentration of 4.2 times 10 to the negative third molar. So we can use an ice table here. Initially, we'll have 0.1 of the HCHO2, and then none of the ions. But now we know at equilibrium, we know what the hydrogen ion concentration is going to be. So we know what the change in everything's going to be because the formic or the formate ion is going to change the same amount. It's going to increase by that same amount. The formic acid is going to decrease by that same amount because the dissociation equation would just be 1-to-1 for all these ions since everything's going to be plus and negative on the right-hand side. +1 and -1, I should really say. So we can fill out the rest of this ice table. And then, whoops, I did Kc here. It really should be Ka. Ka. But we've got the concentration of those ions on the top. And then I just subtracted that 0.0042 from our original concentration to give us the formic acid concentration on the bottom. And what we're going to see is we'll have an acid dissociation constant of 1.8 times 10 to the negative fourth. And this makes sense because we've got a lot more of the reactant than we do the product. So we should have a very, very small number here. And then with the second part, oops, I didn't include that one here. But with the second one, if we just think about part over whole times 100, we could do 0.0042 divided by the 0.1, and then just multiply by 100 to get that percentage. I just forgot to include that here. But if we think about it, if we divide by 0.1, that'll move the decimal to the right one. So we'll have 0.0042. No, that'll move the decimal to the left rather, because we're going to make it smaller. And then if we multiply it by 100, we'll move it back to right. So I think we should get 0.042. Oops, 4 came out really bad. Let's make sure that makes sense. 0.0042 divided by 0.1. No, it was right initially, duh. Yeah, so we'll have, if we divide 0.0042 by 0.1, we'll get 0.042. And then when we multiply it by 100, we can move that decimal 2 more. So we'll see that in this case, we get 4.2% of this substance actually dissociating. So again, still have a lot. Oh, that should have been pretty obvious if I just actually looked at this number and compared it. But again, it's a weak acid because we're going to have the vast majority of it stay as that molecule initially, rather than the dissociated ions. And then with the last one, I think, for this video, is going to be with hydrogen cyanide, so HCN. And we want to figure out the pH if we've got a 0.2 molar solution. And we know the Ka, so that acid constant is going to be 4.9 times 10 to the negative 10th. So we're going to have a very small equilibrium constant because, again, most of this isn't going to dissociate. So we'll have most of it staying as HCN and just a little bit of that hydrogen ion, just a little bit of that cyanide ion. And in this case, we're going to have to use a variable to actually figure out what it is because we don't know the equilibrium concentrations. So when we look at our ice table, we'll have 0.2 molar to start, none of the ions. And then at equilibrium, those will be equal to X, just because we're going to have some variable there. We don't know how much this is actually going to change by. But if these increase by positive X, the original acid is going to have to decrease by negative X. So we can plug this into our Ka expression. And just like the previous chapter, since this is going to be a very, very small number, we're going to get very, very little of this actually dissociating. So to make it easy on ourselves, we can essentially ignore the bottom part. It's going to be negligible. We could do 0.2x, 0.2 minus x, excuse me, cross multiply, get everything on the same side, and then use the quadratic formula. Would be a little bit more precise, but in this case, since it is such a small Ka value, it's going to be a very negligible change. And when we do that, we can see that the hydrogen ion concentration, so when we actually solve for X here, just cross multiply and then take the square root of both sides, we're going to get a concentration of 9.9 times 10 to the negative 6th. So when we then take the negative log of this concentration to convert it into pH, what we're going to see is we'll have a pH of 5.00. And again, since we've got 2 sig figs here, just based on the information we're given, we have 2 sig figs in that concentration. That means when we convert it to the pH, we're going to want 2 digits after the decimal. So that's why we'd have 5.00 here. And with this, again, always just check your numbers, just see if they seem reasonable. But we've got a very, very small hydrogen ion concentration here. Makes sense since we didn't have a super high concentration of the HCN to begin with, and we're only going to get a very small amount of those ions produced, so it makes sense that we get a very small number. And then our pH, since this is still going to be an acid, our pH still should be below 7, but in this case, it's not too much below 7 because it's a weak acid and we don't have a lot of that H+. So if we just think about our numbers, even if we just think about the numbers, we can at least make sure that the numbers make sense for the context of that question. If we get something way different, so if we wound up with a pH above 7, that'd be a basic solution, which just wouldn't make sense for this question. So we would just want to go back, check our math, and try to identify where we went wrong. So we can at least use that as a little bit of a check just to make sure we're on the right path. And with it, that will be the final one for this video. And then we'll continue to look at practice ones as well as different topics related to acids and bases going forward.